I have not got a chance to look at the. So, well, let's get started. No need to copy this. This is just really come from the notes from last week. There's nothing really new there. So, we have started talking about learning theory, right? How much can we learn from our data? That means we have to compare what we can learn, which is expressed by E in, our learning error during training, and we have to compare that with what we can know in the outside world when we get the data point that is we have not seen before, right? So therefore, overall, mathematically, we expressed this last week in this form. We have a bunch of data points, n points. We assume that they are independently generated from the same distribution P of x, right? And then we have the hypothesis, and we want to know, is this hypothesis good or not? Whether good or not, meaning, well, whether the training error and the test error, are they similar or not? Yeah. So we have to define this error per sample point, and we know when we, because it's classification, yeah, our definition of the error will be simply the indicator function, whether our prediction is in error or not, right? Whether this true label yn is not equal to your predicted label, which is given by this hypothesis g of xn, right? G of xn is your estimated label, right? The estimated label given by this hypothesis g. And this indicator function, of course, only takes value 0 or 1, and we know that then by definition it is a Bernoulli random variable. Yeah? Again, no need to copy this. It really comes from last week. Everything is posted online and so on. Really no point to waste time to copy this. So we have seen that this E in, of course, by our definition, is the average error over the sample points that we have, over the training sample points. So this E in is the average of those errors, and therefore it is so-called sample mean. Just a fancy way of saying the average over the samples that we have. Yeah? And these are ID Bernoulli random variables. That this error, each one of them is a Bernoulli random variable. They are ID, means that they are independent and identically distributed, right? So in fact, because these data points are independently generated, so this, whether you take 1 or 0, they're independent of each other, right? Okay? So you have an ID sequence of Bernoulli random variables, it's just taking the average. So therefore, we know that this one is a function of random variables, right? It is the average of random variables. Therefore, E in is a random quantity. Itself is a random variable, yeah? The in-sample error is a random variable. It's different every time you get a different set of data points for training, right? It just so happened that at random, you get this set of data points. But the next time you do the same thing, you get a different set of training data points, you get a different E in. For the same hypothesis, yeah, for the same G, you can get a different value every time, right? Yeah, so that's why this is a random quantity. Okay, everyone okay? Everyone with me? Yeah, we're still reviewing what we discussed last time, right? And then we look at the out of sample error, yeah, the test error. We have to define it by this expectation because we don't know which sample we'll get, right? We don't know in the real world which sample we'll get. It's all by random, right? We assume that this data point that we get for testing is taken from the same distribution as training, yeah? It's a random thing, yeah? Since we don't know what this P is, and we also don't know what is the true label, right? The most we can say is just let's say, well, let's say look at the expected value of this indicator function, right? So at the end, we have the indicator function of this Bernoulli random variable, yeah, which has the same statistics as those training Bernoulli random variables, right? Because they come from the same P, yeah? Same statistics of the Bernoulli random variables as the training. And also, of course, this expectation for the Bernoulli random variable equals the probability of that event itself, right? Okay. So, but this is an expectation of a random variable. Expectation variable, it's just a constant, right? It's a deterministic. There's nothing random about expectation, right? Yeah? No matter which sample you get the same expectation, yeah? No randomness there at all, okay? They are all the same distribution, yeah? Yes?
So the one that was like only one part P, like X wiggly.
Yes, yeah.
So that is the distribution of that random variable.
Yeah, that's a distribution. Yeah, double bar is a probability. That's how we do it, yeah? Okay, so it is the expected value of those Bernoulli random variables. It is also called the true mean. Yeah, right? It's the real mean value of this distribution, right? Which we don't know because we don't know the distribution. Yeah, we also don't know the target function. So there's no way we can know the distribution of this Bernoulli random variable. Yeah, it's an unknown thing, but we know that it is deterministic. Yeah, it is just a constant, just a true mean. So therefore, our question is: this is a sample mean that we can get during training. We can design our algorithm to minimize this sample mean, but is this close to the true mean or not? Yeah, right? So the pack learning question is, under what conditions are these two close to each other? Now, again, because E in is a random quantity, random variable, E out is a constant. You cannot just say they are equal like that, right? Okay? So the only way to discuss this, how close they are, you have to use two quantities, yeah? How close they are, approximate, how good is approximation, and then under what probability that is true, yeah? So that's why we have the pack learning, probably approximately correct, yeah? If they are equal, then they are correct, right? And then if they are approximately correct, then this is approximately, but here always carries probability, just like the picking of a ball from the jar example that we discussed last time, yeah? There's always carry a certain probability there. You cannot escape this because you have a random quantity E in, okay? Right? This is where we are so far. Everyone okay? Yeah, any questions about this? So because we have Bernoulli random variables everywhere, right? So it pays to have a bit of a review or maybe something new as well today. We'll focus on what happens, how can we analyze a sequence of Bernoulli random variables, okay? I asked you to try to review a little bit over the weekend probability, right? Maybe, hopefully you have done some. But today we have kind of mixture, yeah? I know from yesterday, the other session is that most of you have not seen a sequence of random variables in ECE 302. I think the year that you took this ECE 302, maybe the professor did not cover a sequence, basically more than 2 random variables. You certainly should have seen a pair of random variables, right? Maybe you have not seen more than 2 random variables. What happens? Okay, but so therefore today we're going to have a bit of a new, a bit of an old, yeah. So sequence of IID Bernoulli random variables. So we usually Bernoulli random variable, if we want to map it to some kind of physical experiment, a very common experiment is either toss a coin, yeah, either heads or tail, or picking a jar, picking balls from a jar, whether it's red or blue, red or green, let's say, yeah? Okay, so let's use that. So we have a jar with infinitely many balls. They are either red or green. Yeah. And then suppose we define this mu as a fraction of red balls in the jar. Yeah. Of course, this is an unknown. Yeah. You can't even check all of the balls, right? There are infinitely many balls. Yeah. It's in fact not knowable. Yeah. Not just unknown, it's not knowable. So how do we estimate this mu, right? That's the question. And as we discussed last time, well, you try to take some samples out of this jar and observe the fraction of red balls, right? So therefore, when you take samples, then we say, well, we can draw them one by one. So for any random draw of a ball, we can define a Bernoulli random variable, right? Let's define Z, this capital Z. It's a random variable is 1 if the ball is red, is 0 if the ball is green, obviously. Yeah. Then clearly, Z is a Bernoulli random variable, right? Because case value is 0 or 1. It's a Bernoulli, and it's a Bernoulli random variable with the parameter mu, right? Meaning the probability that's 1 is mu, right? The probability that is green is 1 minus mu, yeah? Because that's the fraction, right? So in other words, if I want to take the expected value of Z, which is also equal to the probability, Z is equal to 1, right? As we have seen before, last time. The expected value of Bernoulli random variable is just equal to the probability that the random variable is 1. Simply equal to mu, right? And of course, this is the true mean that we want to estimate. Yeah, essentially our E out, right? Okay. And the proposed method to estimate this is to take n balls out, yeah, and observe the fraction of them that are red, right? So for n independent draws, and they also have the same likelihood of getting a red ball, right? Because we have infinitely many balls there. Taking a ball out doesn't change anything for the next ball. Yeah. Let's say, suppose our outcome is a sequence. We denote them by Z1, Z2, da da da, right? Yeah. Of course, they are RID Bernoulli random variables with the same mu, right? Yeah. I hope this is pretty obvious so far, right? Yeah. So how do we estimate the mu? Well, we're going to define this thing. We're going to take the fraction, right? So Vn equal to 1 over n, this sum, like that. Why would this be an estimate for the fraction of red balls? Well, n will be the total number of balls that we take. What is sum of Zn? Yeah, total number of red balls, right? It's 1, otherwise it's 0, yeah? So this is an estimate that we have already studied last time, estimate of mu after n draws. Yeah, it's an estimate. And of course, this is also called the sample mean, yeah, because it's the average of this random variable, right? Yeah, average of n samples of this random variable. Okay, so of course our question is, under what conditions is this sample mean close to the true mean, right? When is this a good estimate? Yeah? Right? Okay. Hopefully, the more samples we have, the closer we are, the better estimate we get, right? Yeah, that would be our intuition for this problem, just taking balls and check what fraction are red, right? I hope everyone has the same intuition here, right? The more balls you sample, the better estimate you get, yeah? But how can we show that? How can we mathematically prove that? Yeah? Okay. So let's look at a quick example. Say mu is equal to 0.6, yeah? Just the true mean, just a constant, right? Not random at all, say that's true mean. And then let's say the outcome of this draw is, let's say n equals to 9, yeah, 9 draws. The first one is a red ball, green, green, red, 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 green, green, red. Yeah, how about that? Okay, these are the n equals to 9, yeah, 9 random draws. Okay, so this is one random outcome. Yeah, every time you do this, of course, you get a different random outcome. Suppose this is random outcome. Then what would be your output, the estimate, Vm, yeah? Okay. So I guess, let's say this is the mu equals to 0.6, the true mean. We don't know what it is, of course. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 draws, right? Yeah. So the first draw, we get a red ball. What is a Vn or V1? Yeah, what is V1? The average, yeah, there is just 1, right? So it's pretty high up, pretty far away from the true mean, but that's okay. We won't have one ball sample, of course. You don't expect to be very good. How about the second draw? Yeah, we get 1 red ball out of 2 draws, so half, so 0.5, around here. Yeah, right? How about after the third draw? We have third draw is a 1 red ball out of 3 draws, right? So 1/3. 1/3 is, I guess, around here. Yeah, so that's Vm after the third one. So V3, right? What is V4? We have 2 red balls out of 4 draws. So we'll go back up to half again. Yeah, is everyone okay? Everyone following this? Yeah? The math is pretty simple if you know the pattern, right? And then after the 5th draw, we have 3 red balls out of 5 draws. 3 red balls out of 5 draws. Now we have exactly 0.6. We're lucky, right? 0.6, but still, of course, we don't know at this point. We actually get exactly the right estimate, yeah? You wouldn't know for sure, right? Even though you hit it. So anyway, after the 6th draw, you have 4 out of 6. So we have 4 out of 6, 2/3. So it's a bit higher up, maybe right here, yeah? 7th draw, we get 4 out of 7, yeah? So a bit lower, I don't know, a bit higher than half, so that's here. 8th draw, we have 4 out of 8, so half again. Is that right? Yeah, and then the 9th draw, we have a bit higher, I think, yeah, because it's 5 out of 9. Okay, so a bit higher like that. Yeah? Okay. Yeah. So 5 out of 9, right? Yeah. Is this above 6 or under 6? No, it's below 6. Below 0.6. Below 0.6. My notes is I was an idiot. Yeah. Okay. So you can see this Vn kind of fluctuates, right? The hope is that if you have many tries, eventually this thing maybe get closer and closer to mu. Yeah? But is that true or not? Yeah? So, and by the way, this Vn is also random. Yeah? Every time you try this, you get a different sequence of outcome. Yeah? Every new 9 draws, you get different sequence and you get different blue dots. So it's a random variable that we have to deal with. Oops. one thing to know is that Vn is a random variable. So therefore, we can discuss its expected value. Yeah, what is the expected value of this Vn? Well, it is expected value of just definition. Yeah, 1 over n, summation n goes from 1 to n, Zn. Yeah? And expectation is a linear operator, so you take the 1 over n outside, and then you put the expectation inside the sum, like this, right? Yeah. Now we're all set, yeah, because EZn is equal to mu, yeah. That's the property of this Bernoulli random variable, right? It's mu, and then mu times n divided by n, basically, yeah. So therefore, it's equal to mu. What does this say? The expected value of your estimation. This is estimate, right? Vn is an estimate for mu. It's actually equal to mu. Yeah. This is good or bad, or that doesn't matter. It is good or bad. We are trying to use Vn to estimate mu, right? It's good, right? Yeah, because that means that Vn is centered around this mu, right? Yeah. So you don't want this expected value of Vn to be not equal to mu. And there's a name for this goodness, this property called unbiased. Yeah. So Vn is an unbiased estimate of mu. Okay. So unbiased. Yeah. Okay. Now, how about the variance? So if you want to find the variance of Vn, so of course it's the variance of this average. Anyone tell me, how do we find this variance? What do we do to the constant factor? We take it out, square it, yeah? Don't forget, expectation is linear. You just take 1 over n out. But for variance, it's a quadratic thing, right? So you have to take the square of any constant. And then you have the variance of the sum, yeah? But variance of sum, but this sum is a sum of independent random variables, right? For independent random variables, variance of the sum equals the sum of the variances. Right? Remember that property from ECE 302? Yeah? And what is the variance of a Bernoulli random variable? There's a formula for it, right? It is the second moment minus the expectation of the random variable square, right? Which is mu square. But what is E of z square? Z is a 0, 1 random variable, right? E of z square is equal to E of z. Yeah, there's no difference. So this is simply mu minus mu square. Yeah? So if you forget about how to find the variance of a Bernoulli random variable, this is the review for you. Yeah? So therefore, inside it is just n times this variance. Yeah? So cancel out one of the n outside. So we have 1 over n mu times 1 minus mu, right? Okay. Yeah, everyone okay so far? Yeah, with this? So what do we observe then for this variance? It decreases as n increases, right? In fact, it converges to 0 if you have infinitely many samples. So as n goes to infinity. Now, is this good or bad? Or doesn't matter? Why? Exactly. Yeah, when the variance goes to 0, that means your random variable is no longer random in some sense, right? Yeah, you just, the random variable has no randomness, it's just exactly equal to the mean value. Yeah? And this is called consistency. So it's a consistent estimate. Vn is a consistent estimate of mu. And combining both, that means what? Well, this one says that the random variable is simply equal to its own mean value. And the unbiased says, well, this own mean value is actually equal to the true mean. That means this random variable Vn is exactly equal to mu, right? In some sense, yeah, as n goes to infinity. As n goes to infinity, this random variable Vn simply converges to its own mean value, which is equal to mu. Yeah? And this is called convergence in the mean square sense. Okay? So we say hence Vn actually converges to mu in the mean squared sense because it's a variance that goes to 0. Yeah. As n goes to infinity. Okay, so this is fantastic, right? When you have both properties for an estimate, unbiasedness and consistency, that means that your estimate is good. Yeah, when you have more and more samples, you really get closer and closer to the true mean that you want to estimate. Yeah? Okay. So everyone okay so far? Yeah? So it turns out that we can go one step further to claim that, well, this also implies that we have convergence in probability, that we can bound the difference between Vn and W and mu, yeah, with high probability. So convergence in probability. And by definition, convergence probability means that the difference between these two, yeah, is bounded by mu, converges to 1 as n goes to infinity. And this is for all epsilon that you want. Okay. So no matter what epsilon is, I can tell you that I can get that close to the mu. Yeah, epsilon basically is the gap between these two things, right? Yeah. No matter how small epsilon you get, I can make this probability go to 1, yeah, as n goes to infinity. But this probability simply says that they're epsilon close, right? So let me scroll up a little bit just to copy this figure over down there. Paste. Ah, nope, wrong. So how do we indicate this? Let's say a small bound around the mu, right? So this would be mu plus epsilon, and then this would be mu minus epsilon bound, right? Okay. So basically, what this saying is that I want my Vn to be within this bound, right? For some given epsilon. Yeah, that means the distance between Vn and mu is less than epsilon, right? Yeah? The event inside the probability basically is the same as saying that Vn is inside this bound. It's that close to mu. Yeah? And this conclusion says that as n goes to infinity, yeah, I can guarantee that with probability close to 1, yeah, approaching 1. Yeah? I can guarantee, yeah, with probability 1 that we are that close. And this is true no matter what epsilon is. You can make this gap as small as you want. I can get there as long as I have n large enough. Yeah? So this is what convergence in probability means. Okay? But how do we know that this is true? Yeah? How do we know it is true? Okay? Why is this true? Well, we bring back a very important theorem that you have learned in ECE 302, the Chebyshev inequality. Yeah? So how do we know this is? How do we draw the connection between what we have shown, the consistency and unbiasedness, is the Chebyshev inequality. Chebyshev inequality. Remember, you must have learned about this, right? There's a Markov inequality. There's a Chebyshev inequality. Yeah, you might have learned about the Chernoff bound, but that one may not. Yeah, but Chebyshev definitely you have seen in ECE 302. Yeah. It says what? The probability of any random variable being away from its mean value, in this case, being equal to mu, it's more than epsilon away from its mean value. Yeah, that probability is upper bounded by its own variance divided by epsilon squared. Yeah, this is true for any epsilon that you set. Yeah. I hope this rings a bell to most of you. The Chebyshev inequality. Yeah. Basically, it says that a random variable cannot be too far away from its own mean value. Yeah, the probability that it is more than epsilon away from its own mean value is upper bounded by this. Of course, the largest the variance, yeah, the more likely it can be further away. Yeah, so it makes sense, right? Have the variance here. Yeah. So what is this equal to? The variance of Vn, we already know, right? It's 1 over n times mu 1 minus mu, right? So this n, like that's the variance, right? From above, and then this epsilon square. Yeah? So that bound happen to be equal to this. Of course, this one goes to 0 as n goes to infinity, right? That's what the Chebyshev inequality tells us. Yeah? But then you compare this one that we have and the one that we want for the convergence in probability above. Yeah? They're the same thing, right? Yeah? This one says that it's greater than epsilon is 0. It's the same as saying that it's less than or equal to epsilon, which is probably 1. Right? They're just complement of each other. Yeah? So that's how we prove that, in fact, our estimate, Vn, satisfies that property, converges to mu in probability. Okay? Everyone doing okay so far? Yeah? Okay. So this is what we have seen in ECE 302. And the Chebyshev inequality, of course, was developed, or at least credited to Dr. Chebyshev, who was a student of Dr. Markov, who gave you the Markov inequality. That was in the 19th century, 18-something, I forgot which year. Yeah. But in 1960, someone called Hoefding, Dr. Hoefding said, I could do better than this. Yeah? And turns out that inequality is better for machine learning, as we'll see why. Okay? So we can do better than Chebyshev. Yeah. We have the Hoefding inequality. And this is in the 1960s, yeah, many years after Chebyshev and Markov. OE here, I just pronounce it in the kind of the Canadian-French Hoefding, right? But it's actually Finnish. Dr. Hoefding is from Finland, or at least his ethnicity originally was Finnish. So OF is this, OE is this character. I don't know how to pronounce it. If anybody knows, let me. Any Finnish here? Or Scandinavian in general, maybe, yeah. Swedish might be similar too, yeah. I don't know. But anyway, Hoefding, yeah, at least for Canadians. So Hoefding says, okay, he proved this bound. The distance between the Vn and mu, the probability is greater than epsilon, is upper bounded by 2 times minus 2n epsilon squared, like that. It's exponential like this. So why do we say that this is a better bound than the Chebyshev inequality. Yeah, as n goes bigger, right? And that's much tighter bound because the exponential decrease instead of 1 over n decrease. Yeah? So this is exponential. N. Okay. And this is particularly important for machine learning, of course, right? Because we're talking about how many samples we have. Yeah, this n, right? How many samples is enough? So you want to have as tight a bound as possible with respect to n in order to do your analysis. Okay. This is note 3, not 2. This is note 3, I think. And then number 4. Now we can go a bit further to talk about the confidence level. So basically, when it's probably approximately correct, that probably, yeah, how confident are we that we have this level of approximation? So confidence level. Yeah. In general, you can, if I plot this figure, let's say, plot the PDF, the density of Fn, this random variable. Yeah, remember, Fn is a random variable, right? We can talk about its mean value, but we can also talk about its PDF, density function. Yeah, this just V is just a dummy variable. Okay, usually the density function of a random variable looks maybe something like that with a certain tail like this, right? And then maybe here is the mean value. Yeah, mean value is here, and maybe if you want to bound around this mean, the true mean, this is mu plus epsilon, yeah, mu minus epsilon, right? Like that. And what is the shadow here, the shaded area outside this bound? What is it? If this is the PDF of the random variable, then the shaded area will be the probability that the random variable falls outside of the bound, right? So this is actually the probability Vn minus mu is greater than epsilon, right? Yeah, this is the basically shaded area. Yeah, well, area of shaded region, I guess, more precisely. Area of shaded region. Right? We're going to define this, we're going to give it a name, we call it delta. Yeah? So well, with this definition, then, of course, then the probability that we're within the bound, so less than or equal to epsilon, equals to 1 minus delta, right? In other words, 1 minus delta is our confidence level. You know, we know are confident that our answer, our estimate is within epsilon, away from the true mean value that we want to estimate, right? Is the confidence level. Yeah. Because that's the probability, yeah, that we have derived within epsilon. Yeah. And this, very often we call this region where the distance is less than or equal to epsilon. So this part, yeah, this is called the confidence interval. Okay. So with 1 minus delta confidence, our estimate is within the interval that we want. Okay. Yeah. Everyone still with me? Any questions? So then, given this, well, remember our Hurstring bound. Hurstring bound is this one, right? Yeah, this one. So if we set the right-hand side to be equal to our delta, right? That's the worst case delta, right? The worst case delta. This is the Huffington bound says it's at most that one, right? Yeah, let's set this as the worst case and see what happens. So Huffington bound gives us that in the worst case, delta is equal to this 2e minus 2m epsilon squared, right? Yeah? So this, of course, we can say that, well, I can solve this for epsilon as well, right? So if I given the delta and I ask for what is epsilon, then this will be 1 over 2m log. This is natural log, as always, if we don't specify it, over 2 over delta. Yeah? Right? You can see that epsilon and delta are kind of in opposite directions, right? If you have a larger epsilon, then you need to set a smaller delta here. Yeah? So if you have a larger range, then you can have a smaller delta, but then you have a higher confidence because 1 minus delta is the confidence level. Yeah? So therefore, larger epsilon is the same as saying we have smaller delta. In fact, you can go the other way around as well. And this is the same saying that I have a higher confidence level. Right? Does it make sense that we have this higher confidence if I set a larger epsilon? Does it make sense for estimation? Yeah, if I want to be more loosey-goosey, right? I mean, I can just, my estimation is a bit loose, then I'm pretty sure that's within that range. But then if you want to set a very tight gap, then say, okay, I'm not so sure that I can get to that point at this time, right? Depending on what my n is. Yeah? So let's look at a numerical example. Say, suppose we want delta equals to 0.01. Yeah? That means what? Our confidence level is, what is our confidence level if delta is 0.01? 99%, yeah? Pretty sure, right? Pretty good confidence. So we want to make statements for which we are 99% sure to be true. That's what we're saying, yeah? So what kind of statement can we make? Yeah? What kind of epsilon? Then this epsilon, of course, equals to 1 over 2m log of 2 over 0.01. Yeah? Again, we're dealing with probability, right? So we can never be sure about anything. Everything we have to say that, well, I'm pretty sure. Yeah? Nothing is 100%. Yeah? You can get 99%, you can get 99.999%, but nothing is 100% really. So this turns out to be 1.63 over square root of m. Yeah? Okay? So what does this mean? Yeah? Like that. So if I plot this figure, again, the Vn versus n, how many data points I need? Okay? So let's say, again, mu is, let's say it's here. Yeah, that's the mu that we want to estimate. So I want to draw the confidence interval. Yeah, so mu plus epsilon above and then mu minus epsilon below. So what does it look like? Well, epsilon is this, right? It is curve that looks like that over, well, like this, over m. Yeah, so therefore mu plus that, I get something above like this. So I'm going to get a curve that looks like this, if I can draw properly. Yeah, like that. And this will be mu plus 1.63 square root of n, of course. Yeah, that's mu plus epsilon. Yeah, and below I have something that's symmetrical. Not quite symmetrical. Close enough. No. Like that. Yeah. Not my day of drawing. But anyway, mu minus 1.63 square root of m, like that. Okay. So what does this tell us? The more and more sample I have, my confidence interval gets smaller and smaller. For the same confidence level, right? 99% sure, that my estimate will be within these blue bounds, right? I'm 99% sure that I'm within these blue bands. Depending on how many samples I have, if I have fewer samples, then this band will be wide. But if I have many, many samples, then my band will be very, very low. Yeah? Again, for the same confidence level, yeah? I'm 99% sure that my estimate will be that close to the true mean value. Yeah? That's what this thing says, right? So again, this is for the, I'm plotting the 99% confidence interval. As you have more and more samples. Yeah? So nobody should be surprised that this confidence interval gets smaller and smaller after our analysis. Yeah? Right? So in fact, as n goes to infinity, of course, these two bounds approaches mu, yeah, itself, then you get with 99% confidence that you get exactly mu, right? Or as close to mu as you want. Okay? Any questions? So far what you have seen is that when you have a sequence like this, and then we have to talk about how good is the estimate Vn versus the true mean mu. Again, we always have two things, right? The confidence level and then the confidence interval. Yeah? So the confidence level tells you the probability. The confidence interval gives you the approximation, how far away do you allow the estimate to be? Yeah, there are always these two quantities together. Yeah, you cannot just talk about one without the other. Yeah, and remember why we talk about this at all? Why do we talk about this sequence of Bernoulli random variables? Because from the very beginning, if I may go back, these are the Bernoulli random variables. Yeah. Our E in and E out are the sample means and the true means of those sequence of Bernoulli random variables. So armed with this new knowledge about how good the E in, basically the E in can approximate E out. Yeah, we have to go by this type of analysis. Yeah, so next time we're going to put this together and see what we can say by using this theory. Say about the quality of learning. Okay, there's a quite a twist and turn later. Okay, it is not so simple, but this will form the foundation for our analysis. Okay. Yes. Yes. Exactly. Yeah. Yeah. Expected error. Yeah. So we'll continue tomorrow. Yeah. So see you then.